Okay, so this this is, let me go to the terminal. Um, this is C++ because I know you weren't here, Jason. We talked about, as a quick summary, we basically talked about differences of C++ and other languages.
Yep.
That it's, you specify the types, you manage the memory.
Yep.
We also talked about how data is stored in the memory,
Yep.
with the heap and the stack and like things like that you may have heard before.
Yep.
And I was starting to talk about, I had showed a few examples of pointers and references and how you can basically put and manage memory throughout the stack and heap. But then we
Yep.
started talking about basically data structures, and I think that's where
Yep.
we kind of ended, was we were focused on data structures. And there, if you look at a high level, view of things, there's really three types of data structures. There's like linear data structures, associative data structures, and then user defined custom data structures that are more complex. Linear data structures are basically like, conceptually, your data is in a line. And associative container structures are basically, your data is like a key value pair type of scenario. And so, you can think of like a linear data structure as like an array or a list or a vector, but like basically something that's just in a sequence together. And you're going to operate on it in a way that is in sequence. Associative containers are like, used to like, they're not all ordered, but you have basically a key that you're going to use to extract information from the container of a certain type. So think of like a map where there's a key and there's a value. It's called a key value pair. And if I take my map object and I put in the key, it returns the value that's in the object. And so at a high level, those are the primary types of data structures that you're going to use. C++ also lets you build custom data structures. And so you can build like a data structure that has like various attributes, kind of like classes, but without functions, just like the data itself, just the members, just the variables. And you can create and use those, which are very useful. So I think what we had done was we had showed a couple examples here of an array, and the array basically is specified. This current array that you're seeing right here is specified as a 3-element array, and it's predefined right here of A, B, and C. And then you return it with the index, and basically the order. You return the element you want based on the order it is, and everything starts with 0 in programming. So like element A is at the 0 index, element B is at the 1 index, and so on and so forth. And then we talked about like same thing for an array. You can loop through the array, and with the index, you can print out the information from the array and kind of make the index your variable that gets incremented in C++ for a for loop. So for loops are, start at 0, go until it's less than 5, and then increment by 1, I by 1. So that's an array, and an array is fixed when you create it. The size is fixed. So you can't take an array that's a 5-element array and make it a 6-element array. You would have to copy all of the data from the 5-element array into the 6-element array, into a 6-element array, a new one. You can't edit it to create more components. And a vector is a lot like an array, but you can edit it to create more components. So you can append and keep adding on. It's not a fixed size. It can grow in memory, but it's still this sequential item. And so you can push elements onto the back. You can pop elements off the back and shrink and grow the array or the vector. A list, we were just talking, I was just getting to a list, I think, when I was talking to Rachel the last time we did this. And I believe a list in C++ is, there's a couple different types of lists in general. I can look up what this one is in a second, but from a list perspective, there are, a list is really just like a bunch of data that's stuffed into memory in random locations. And so you can, and I have a good visual example that I had built here. An array is like fixed in memory. Like if you think of memory as this giant block of a matrix, it's fixed in memory. And if you think of an array, it's like 111 is filled. Like those are the filled cells. And then for a vector, if you look at the matrix block of memory, like 111 is filled. But you could also fill this an additional one if you wanted, where you can't do that with with an array. And then a list is just scattered, right? So it's just kind of all, everywhere. It's not directly necessarily in a sequence or in a line. And I'll get to why all these different structures matter and what they're good for here in a second. But the reality is that for a list, what you have is you have the current cell and a pointer to the next cell. So that's how it knows it's in a sequence together in kind of a linear sequence, is because like the actual data structure of a list has like the memory address of the first element, and then it has a memory address of the second element, and so on and so on. Doubly linked lists have like the reverse. So like, in a regular list, you can go forward. In a doubly linked list, you can go backwards as well. So you can iterate. You could start at one element and kind of go backwards and forwards. So there's some differences between the different types of lists, but they are a linear sequence from your perspective of like, I'm kind of iterating through them, but it's all scattered in memory and kind of nonsense. And you just bounce from element to element to element to element as you're going. You may not notice that as the user, but that's what's happening behind the scenes. And so there's these things called iterators in C++, and it's basically a data structure that has like internal like for loops and while loops. And so for a list, you kind of just iterate through the list, and an iterator will then like print out like the entire list. You don't need to know a whole lot of details there, but what I wanted to get to and why I wanted to talk about these kind of three things. Again, these are all linear. These are not maps. The reason I wanted to talk about these is there's something that I had mentioned really early on that I hadn't really got to, which is big O notation and computational complexity. And you can think of this as the amount of time it takes to run an algorithm. And it's something that's very important in computer science, especially when you get to large amounts of data. It's the same reason why if you have, a bunch of nested for loops and while loops, it's computationally inefficient, because, now I have to loop through once, and then I have to loop through, 10 times, and then I have to loop through a second time, and then I have to loop through 10 times, so on and so forth. Big O notations really matter for computer science, and the speed at which an algorithm runs really matters. And C++ is really good at exploiting all of those things. So from a data structure perspective, ignoring the loops for a second, the data structures have different big O notations for different operations. And if you look up Alan Turing later, who's like the father of computer science, he talks about basically, Turing completeness and all these different things that describe what a computer can do. And at the basis, it's basically like insert, read, delete, or change. Those are kind of the operations that you can do on a data structure. So if I have, for example, let me just grab this little array right here. Let's say it's a little array. I can insert in here, or this little sequence data structure, I can insert by adding an element. And I can add that element anywhere in the list, right? In this like ordered list. I could read an element. So I could come in here in memory and say, hey, what's the element at the 5th index or 4th index? I could delete an element where I delete that element, and now the list only has 5 elements. And so I could also change it where this is a 1, I could go in and change it to a 0. So these, operations that you can do on these data structures, Alan Turing kind of defined really early in the computer science world, and uh, gave us kind of a way to think about how algorithms run. So, we have these three data structures. We have an array, a vector, and a list. If I have an array, um, reminder, this is the fixed size, right? But it's sequential in memory. If I want to, let's just do the operations for it. If I want to insert something in here, am I able to do it? It's like kind of an open question to you guys. Delete and change. The answer is, for this one, you're not able to do it because an array can't be changed. So this is not a valid operation for an array. Read is a valid operation because I can go to any index in the array and I can read it. Delete is not a valid operation because I can't change the size of the array. I can override it, I can make it 0, but I can't delete it. And change is a valid operation. And so each one of these, I'm mixing a lot of things because I'm like remembering as I go. Each one of these things, each one of these structures has valid and invalid operations in terms of what you can do with a data structure. But what's interesting is, though it might have some invalid operations and a vector might let you do those things, there's a difference in read and lookup time between like an array and a list. So if I have an array that is 1 million elements long, right? It's just this humongous array. And I want to look it up. I want to look up the 129,000 element in the array, right? I return it in what's called a big O of one time, which means it takes one step, one operation to look it up. And it's literally just like, my array, 129, thousand or whatever, that element. And so it's a constant time operation, and it's a constant time of one operation. The next version of this is big O of constant time, which is like it's more generic than like an operation, but it's still constant. So it might take 2 steps or 3 steps, but it's always 3 steps. It never changes. So these are kind of equivalent, but one is more like specific. So this operation for read is big O of 1. And likewise, the operation for change is big O of 1. Or big O of 0. Does that make sense? I'll get into what the other big O's are here soon. Might be kind of confusing, so I'm happy to rehash some stuff. Can you guys hear me? You're muted if you're talking.
I was also muted. Yeah, that makes sense.
Okay, cool. Then the next thing to know is that there's a big O of what's called N, which is polynomial time, is linear time. So this is constant time. Big O of C is constant time. Linear time. So if I wanted to search this array, so I didn't talk about that, but like search would be like, I want to go through the array and find out if an element is something else. Search, you could validly search an array. That's easy, but it's a big O of N time, because I now have to search through every element and compare it to something else to see what it is. There's also these things called sort. which is a fancy algorithm to, there's a bunch of fancy algorithms for sorting, but sorting algorithms are like, if I want the array is like randomly mixed, but I want to order it from like lowest to highest value. Now I have to loop through it and begin this like ordering sequence um, of like changing values and stuff. So what you can do is use different types of sorting algorithms, and they can range from like higher big O's to big O of like uh, log n. I think Rachel, you might have mentioned that like n log n or something. Um, I'll get into those like later on. We don't need to worry about it now, but there's lots of other big O's. Then there's big O squared, which is like if I want to search with a something called switch search, which is like this is polynomial time now because it's raised to the power of 2 is a search time, so it's called polynomial time, and it's basically like I want to order the list, and I want to order it by comparing the first 2 elements and switching them if they need to be switched to get it in order. And I just keep doing that, and then I loop again, and I keep doing that. Well, the worst upper bound of that, I believe, is n squared time for searching. And there's a bunch of different algorithms to do these different types of times. I'm just kind of like introducing you to concepts here. And then there's like way worse versions, like e to the n, which is like or exponential time. And there are algorithms that are exponential time algorithms. And think of, I'll give you an example of one that's like highly complex like this. It is chess. If you were to search through all the combinations of chess, there are more combinations in chess than there are atoms in the universe. And the way in which the trees branch for just those 64 squares and 32 pieces, like moving around. I think I said 30, maybe it's not 32. Yeah, it's 32, I think. Pieces moving around. Those combinations, that algorithm to solve that correctly is like greater than polynomial time. So it falls into like, an exponential time category. And so my whole point with like starting to introduce you into these, and I'll go over like list and like vector with respect to these next time we meet, is to introduce you into building efficient programming and the upper bounds on like algorithms in mathematical science. Linear time might not seem like a big deal, but it's a big deal if I have 10 billion elements, if I can do it in constant time instead. N squared might not seem like a big deal if I have 10 elements, but if I have a billion elements, now that becomes super complex. So if I can find an algorithm that does it in linear time, that's way better. And, likewise, exponential time, if you can find an exponential time algorithm that does it in polynomial time, you'll become rich and famous. And it's infinitely better. Now, this gets to like one of the deepest questions in computer science that I'll leave you with, and I'll send you a video after this, which is a phenomenal video, which is does P equal NP? And you may have heard this famous problem before, but what it stands for is, does polynomial time equal non-polynomial, non-deterministic time? There's a fancier word for it, but basically non-polynomial time. And we'll come back next week and kind of talk about this. But this is a famous mathematical computer science problem. It's one of the Millennium Prize problems where you get $1 million if you solve it. And it's potentially the hardest mathematical problem of all time, and is an open question. And we'll probably talk a little bit about that next week. But it's intimately tied to increased computational complexity. And we don't know if there's algorithms that are for non-polynomial time problems that could translate those into polynomial time problems. We're still not totally sure.